All right, so this is a lesson on semiconductors, the point, and so on. Um, okay, so uh, we're going to start with the periodic table. Uh, you guys in your science classes, you've learned there's a staircase on that periodic table here. This is an important section. Okay, so those are called metalloids here. Um, while I'm recording this computer is really slow, so bear with me. Okay, so a metalloid, right? So they're half conducting, half insulators. Okay, so they draw a staircase. So right here, essentially, and of interest to us will be this guy, silicon. So conductors are here, right? So the metals, right, and non-metals are here. Okay, I'm not going to get into the chemistry, how they create compounds and so on. This is super interesting, but this is not our topic now. Okay, so silicon. Um, silicon comes just from sand. Okay, from where? Okay, it just comes from sand, from rocks, as it says here. Images. Let's see what I can find. Okay, so this is what silicon looks like. It's super abundant. It's super cheap to get. Uh, and it turns out to be a really cool element in terms of what we can do with it. So, in the BBC video, if you watched it, you learned that silicon uh, was discovered as having pretty cool applications pre Second World War. If I'm not mistaken, I don't know all the details by heart, but if I'm not mistaken as well, in the First World War, I would have to double check that. But anyway, what's of interest to us is diodes. We'll start with diodes. Um, let's actually step. Let's take one step backwards. Let's just go to how we can get to diodes and transistors. So this is what we'll be talking about today in this lesson. So as if I take silicon, okay, so silicon naturally is a crystal. Okay, so I like this drawing. I'm taking those guys because this is much cleaner than me going on my pad to draw. Okay, so I'm just going to use this here. So silicon has 4 electrons on the outer shell. How do we know? Because it's on column. This is always confusing for students. This is column 14, but it's actually column 4. How come? It's complicated. I'm not going to go into this details, but just count where it's how far it is from the left. So 1, 2, and then you skip all of this section here, 3 to 12, because it's on row 3. Right, so anyway, it's 4 columns away from sodium, and it's 4 away from noble gas, argon here, right? Okay, so where does that leave us, right? So it's right in between a metal and a non-metal. So essentially, its properties, it's it's not really a metal, it's not really an insulator. So you can make it act as if it were a metal sometimes, and as if it were an insulator sometimes. It's a crystal, has this shape, okay, so it gives you an array, as they call it here. And then what's going to be interesting, again, they show it in the BBC video. It's in the last section, the last episode. So we're going to do one of two things, and it's called doping. Okay, so what does that imply? So how do we dope? We're going to take either an element to the left of silicon on that column here, on column 13, or we're going to take an element from column 15. So if we go on column 13 and we melt silicon, right, we get it to be a liquid, and then if we inject just a bit of gallium, gallium is especially used. I'm no expert on this, guys, but as far as I understand, gallium is the most commonly used one. I wouldn't be surprised they can do it with aluminum and boron and so on. Okay, but it's regardless, that's not important. What's important is that if you take something like gallium, now gallium is on column 3, right? It's 3 away from the left. And so gallium would have 3 electrons on the outer shell, right? Not 4. And so if you inject just a bit of gallium in the silicon structure, so here they take boron, right? So we're going to go to this one, right? So as you're going to get it to cool back, boron is going to install itself in the structure, but there's going to be an electron missing on the outer shell. This is going to become what we call a hole. Okay, there's an electron missing in the lattice. Okay, so it's going to give that piece of silicon some special electrical properties. We're going to get back to that. This is going to be called the p-type because it's slightly positive because it's missing an electron. Conversely, if instead of putting a column 3 element, we're going to put a column 5 element, like arsenic or phosphorus, now we're going to have what they call an N-type semiconductor. Now notice the phosphorus is here, and now there's an extra electron in the lattice. And so that's going to give special electrical properties to that chunk of semiconductor when it's cooled back. Okay, you're saying that's not in. Why is that interesting? Well, what's going to be happening and what's going to be the interest of this is when we're going to stack, smush together an N and a P-type chunk of silicon. So if I go here, NP silicon, well, there you go. So we're going to get exactly this, okay? So on the left here, if I have a little chunk of P-type silicon joined together with an N-type silicon, I'm going to get the electrical device called a diode. So this is the drawing. You should recognize the drawing. Now there's tons of physics on what happens when you connect a battery to this, right? So I'm obviously not going to go into those details. What's important for us to know, and I'll really keep it at that, okay, it creates an area of depletion if you inverse the current and so on, but this is not what's of interest to us. What's going to happen is if you put a battery to this positive here, negative here, that chunk of silicon, now P and N together, is going to start conducting towards the right. But if you put the positive here and the negative here, so against the arrow, notice, it's not going to conduct. Now that's given some conditions, right? You can actually start breaking a diode if you apply too much voltage to it. Again, that gets really technical. This is not of interest to us. This is just like an intro to semiconductors and so on. So I just want you guys to know the basics of it. Okay, so yeah, so this is what's going to happen. So this is the property, the key property of a diode. It conducts in only one direction, and it's because of how it's built inside. It's got a P and an N type silicon inside. I'm expecting you guys to know that a diode is a P and an N chunk together. and to know that the P will need the plus side to conduct. So if you put P on P and negative on N, it will conduct, and the converse will happen, right? It won't conduct the other way. Okay. Now here's the next thing we can do. Now some of you might have thought of it. If I put an N and a P and then another N, now what is that going to give us? That's going to give us a transistor now. And this is going to be really interesting. Now, let's use this drawing. Let's use this one here to start. I would like to find one where it's flipped facing up. I don't find one quickly. So I'm going to have to use this way, because see the transistor here, they use it up, which is what I was interested in. So what's important in the transistors is that now you get 3 chunks together, okay? And the key property of a transistor is that you can use it as an amplifier. Now, I need you guys to know that, okay? So definitely write that down. A transistor, the key property of it is that it can be used as an amplifier. So I can use this drawing. Now there's this one here that's really nice as well. Actually, let's use this one. Again, I could draw that, but it's much cleaner on these here. Here's the drawing. Okay, so this drawing here. Okay, so what do we get? So you got to picture this as being, there's a chunk of N here, there's a P here, and an N here. But when we use a transistor in a circuit, we don't draw NPN anymore. We just use this drawing, right? Now, why is it drawn this way actually? It's because it actually is 2 diodes facing each other, right? So we just draw one arrow coming out here, but there's another one going up here, if you can picture it this way, right? Because PN, right? PN. Anyway, so the key property of a transistor, it can act as an amplifier, and boy, are amplifiers important in today's electronics. I'll get back to that. So here's the short version, okay, of all you need to know. You see IB here, okay, so IB, sorry, let's go back to this. So the middle chunk, it's called the base. The bottom part, where the arrow here is, that's called the emitter, 2 T's. And the top part, N, it's called collector, okay. And what's going to happen is, oh, we see it here, okay, is with a small current through the base going out through the emitter, you can control a huge current coming from the collector going all the way through the emitter. So essentially, you're going to get a little bit of a current through the base here that's going to control a huge IC collector current going through the whole transistor. And so if you put, and so there's a ratio to this. This is called the HFE, and this is called the gain. Okay, so HFE gain transistor. Okay, we're going to, so I need you guys to know the math for this. Okay, so write this down here. Okay, so HFE stands for gain, and we call it the beta also. Okay, so the Greek letter, it's a nice looking B. Okay, is there another way to? Okay, anyway, I'm trying to go quick here. Okay, so here, right, HFE, beta. Okay, so I need you guys to know this. It's really easy. Okay, it's just application of simple math that you guys know. Okay, so essentially, the beta, the HFE, for each transistor changes. This is what a transistor looks like. This is a baby transistor. There's bigger transistors. Okay, typical values are around 100. It's a range. Okay, so as they say here, okay, so this is a good example, can go from as low as 10 to 500. Okay, typical values that I've seen is around 200, 100. Okay, and simply what that value of HFE, beta, the gain, those are the same things. All it's telling you is the factor by which IC gets controlled by IB. So let's say that again. So let's go to our drawing. So if I have an IB of 10 milliamps, for example, 10 milliamps, and let's just pretend this transistor here has an HFE of 100, right? So if I put, well, let's make it a bit simpler. Let's say I have 1 milliamp here as IB, and my HFE is 100. My IC is going to be 100 times what IB is. So 1 milliamp times 100, so I get 100 milliamps. That's going to go through the whole transistor from or through the collector, right? So it's just a relationship. So IC, so it was written here, IC equals HFE times IB, or beta times IB, it's the same, right? So I'm just going to make you guys learn about that, okay? Yeah, I'm just thinking through my head here. I'm just thinking, is there anything else on this? Okay, so let's review quick, okay? So silicon has really critical applications. It's a super cheap material to gather, to harvest. It's a metalloid, so it's a semiconductor, right? It's between pure insulators and pure metals, okay? We can create special chunks of semiconductors that we call P versus N type. What does that refer to? If I want to get a P type, I will inject it, I will dope it with an element having less electrons, right? That's why it's P, because it's got less electrons. And so if I put a boron atom in it, right? So they dope it with very little concentrations of it, right? So it's mostly silicon, but just a bit of the impurities. So boron or phosphorus in this example. What do you get? You get this, right? A P-type versus an N-type. A P-type is one where you put element from column 3. N-type is one from column 5. Makes sense because it has more electrons, so that's why N negative, P positive. There's no interest in doing this if we don't sandwich those things together. And so you get the diode, right? So a P-type and an N-type sandwiched together. Now there's names to those pins now, right? So the P-type gets anode, the N-type gets cathode as a name. Plus here and a negative here will conduct this way. That's why the arrow this way. Those are good to remember, by the way. Anode, cathode, they're hard to remember. Even myself, I struggle to remember those because they're hard to get a trick. So so anyway, P versus N, that's easy to remember, right? So you put the positive on this side, negative on this side. That's all to know about the diode. Then if we go further, if we add a third chunk of N or P, then we can get an NPN transistor. Now you can also get a PNP transistor. Now it will just have the same properties, right? But inverted, right? But this one we'll leave alone because it's just the inverse. Okay, so you can get PNP transistors. Notice the arrows going in this case. Okay, but I don't focus on the PNP. I'll just focus on the NPN. And then why are transistors so critical in electronics? Now there's many kinds of transistors, as they mention here. There's MOSFETs, there's also JFETs, and so on. These are going to be treated in grade 12 and in your college years or engineering classes in university. But the key function of transistors, and it's the same across the board here for all those other transistors, is one of their main application is to be used as amplifiers. And the key formula for that is the formula I had up here. So IC equals HFE or beta times IB. And what does that refer to? Simply this. If I have a small current going through the base down to the emitter, it controls a much greater current going through the collector right here. And so the relationship between those two is here. Okay. So I think that will be this lesson. Okay. So I'll take any questions on the Google Classroom, okay, or the blog, and we'll go from there. Okay. Thank you. We talk to you later. Bye-bye.